So I'm Krister, and I'm going to talk about my work on finding bugs in GCC. So the thing I'm going to talk about here is SMT GCC, which is my toolkit of random stuff to analyze the internals of GCC with SMT solvers. You can find it on my GitHub. So it consists of some random tools, as I said, but the main thing I'm going to talk about today is SMT GCC TV, which is a tool doing translation validation. So what it does is that it takes the compiler's representation of the program before and after each optimization pass, and it checks that the semantics is consistent before and after. So if the semantics have changed, that means that the program is doing something different, and that is actually a bug that GCC has introduced. You use the tool by just compiling as usual with the plugin enabled. And when it finds a problem, it writes the message something like this. So in this case, a function f1 has been miscompiled. Is the IVOPS pass, the induction variable pass, that has made the function having more undefined behavior than the original function had. And you can see that with passing the arguments that my tool have found here. So to take a look at what's happening here. So we first start with the function. So I reported this as 113703 to GCC. So this function is a sort of a memset with an offset. So to see what GCC have done with it, we must look at the GCC internal representation. So you can get dumps from each optimization pass by providing certain dump flags. So this fdump3 all dumps all 3 passes. There are some other kinds of passes, but this tool only works on 3 passes, so we are fine for now. And as you can see, the program is represented some kind of primitive C kind of thing. So each line has only one operation. Control flow is with gotos. It's on SSA form, so you can only assign variable once. So that is why you get version variables and fee node to combine variables in control flow. So if you're taking a compiler class, that should be rather straightforward. If you're not taking a compiler class, I still think you, in general, can see what the different passes have done. And you can get lots of enjoyment by looking at what the compiler does to your pass, to your function by comparing the different passes. So back to the bug. So to the left, you have the original version, and to the right, you have what the IVOPS pass has done. It's a little bit hard reading all this slide, so I have rewritten it in a C form. That should be easier to read. So again, on the left, the original, on the right, what IVOPS has transformed it to. So you see the original updated 2 variables in each loop, while the IVOPS has instead decided to calculate an end pointer and just update the pointer. So to see what's happening with the values that the tool told us. So the original version, it takes the pointer, subtracts 12 from it, writes 0, updates the pointer, updates I, and then the condition is wrong, so it exits. So it just writes 1 byte to p minus 12. The optimized function, it calculates the end pointer, again subtract 12 from P, writes 0 to P, updates P, but now this condition is actually true. So it continues to the next byte, and next byte, and next byte for 10 exabytes, roughly. So that is why my tool complained that it's more undefined behavior, because this trash memory all over the place, writes over buffers, have aliasing problem, whatnot, depending on what exists in those memory. My tool could have said instead that it detects that memory is different. That depends on a little bit what it finds first. So this is a bug you can find with current GCC, and it has been there since forever. I think it was 4.7 that introduced this. But so what kind of check my tool does is it does 4 different checks. One is that the internal representation of the function after optimization does not invoke undefined behavior for inputs where the original function had defined behavior. With input here, I mean function arguments, but also the state of all global memory. The tool checks that both versions return in the same way for the same input. So if the original function called abort for a certain input, the optimized function should also call abort for that. And both versions should produce the same return value, and after execution of the function, the global memory state should be the same for the same input for the 2 versions. So this example I showed you said it was more undefined behavior in the optimized code. And in that example, that was a serious problem. But just having more undefined behavior is not necessarily a big problem. So you can see I have reported sort of 80 bugs on this. Most of them have new undefined behavior, but many of those tickets have got very low priority. And that is because the GCC developers know that there are no optimization passes after the offending pass that actually can take advantage of this undefined behavior to cause any problem. So for example, if you have some extra signed overflow in the code, that essentially only cause problem if it's used in a context where you have a comparison with 0 and so on. I actually had a talk about that kind of thing sort of 10 years ago on this conference, where I listed all the ways that GCC can optimize programs if you have undefined behavior of this form. But so take an example of one of these really low priority bugs. In this case, we have 2 arrays that we add and subtract a couple of elements. So in this case, the vectorizer has decided to load both arrays B and C as vector operations, add and subtract the vectors, and then extract the elements from it and write it back. And in this case, we have now additional additions and subtractions. So let's say that B1 and C1 has the value int max. That was completely fine in the original version of the function because they are subtracted and the result is 0. But in our optimized program, here they are included in the vectors addition. So they are being added, so overflows, which is undefined behavior. But this element will never be used for anything, and so on. So GCC do not have any opportunity to actually miscompile the program. But it is a bug, and it should be fixed, and it will probably be fixed sort of soon. But it is not a serious bug. So I'll show you a couple of toy examples. So in preparation for this talk, I used my tool to compile the Linux kernel with the current, with the compiler as it was a few days back, and it found a bug. So this is sort of the kind of undefined behavior bug I talked about. For the Linux kernel, it doesn't cause any problem at all. In this case, it is GCC that is confused about alignment requirements. But so the short version is that GCC can only know that it's 32-bit aligned, but it is 64-bit aligned. On the other hand, the structure that is being sent into the function is always 64-bit aligned. So who cares? And GCC doesn't use an instruction that is problematic for that anyway. But it is a serious bug. It can miscompile, especially vectorized code and so on. So it has been fixed already in GCC. And will be backported to GCC 16 soon. I also have a similar tool for the backend. So here it compares the actual compiler's representation of the last middle end pass with the generated assembly. I support ARM, RISC-V, BPF, and SH. SH is the CPU used in the Dreamcast games console. So important target. For ARM, I support sort of everything. My process of developing this is I compile some code, and when my tool complains it doesn't understand an instruction, I add it. So there are several instructions I have not implemented, but they are easy to add as I find them. RISC-V, I support the basic profiles, only half of the vector instructions. And BPF and SH are partially supported. But all of these are complete enough, so I have reported bugs on all of the backends. So most have been fixed. I think the only one that are open right now is this one, where SH miscompiles essentially this function. The backend is doing clever tricks with the condition, with the carry flag to get rid of the subtraction by one and comparison and so on. And the subc instruction does not do exactly what the backend developer anticipated. So take a look at how the tool actually does this. So the main piece is SMT solvers. So SMT solvers are tools to find solutions to systems of equations. So when you give such a system of equations to a SAT solver, it can return one of three different ways. You can say SAT, there is a solution. And it can return one solution to you. ANSAT, there are no solutions. And most SMT solvers can give you a mathematical proof that there are no solutions. So you can verify that the SMT solver actually did not have a bug. And an unknown timeout out of memory, and so on. There are a couple of SAT solvers, SAT and SMT solvers in use, and I use three different in my tool: Bitvusla, C3, and CVC5. Bitvusla is preferred because it's much faster than the other for this use case. So to illustrate how to use the SMT solver, so let's say we want to verify that our target function here is a valid optimization of the source function. So this is, well, completely uninteresting bit manipulations, but anyway. So what we want to show is that the return value of source is equal to the return value of target for all possible input. This is not a good equation to solve for because we want to show it for everything. So we instead ask the solver to give an example where they differ. If they differ, we have found a bug, and the actual values give us an example of, gives a test case where this fails. And if it says that there are no solutions, then we know they are the same, because, well, it has a proof that there are no solutions. And this is quite easy to do with the solvers. So here I'm using the C3 Python interface, because that fits on the slide. Normally I use, as I said, Bitvusla in C++ that needs more code. It's exactly the same work needed, but it's a little bit more verbose. So we start by creating two unconstrained variables of the type bit vectors, so 32 bits. We build up the expressions for each function, and then create a solver with the equation we want to solve. And then print the result. So when you do function here, to a GCC pass, you iterate over the function, instruction by instruction, add this to the expressions as you go. But there are more problems when doing C than this. So one thing is undefined behavior. So let's say we want to, again, show that target is a valid optimization of the source function here. But here we cannot check that it's the same for all values because source is not defined for x is 0. So we handle this by keeping track of each instruction we added to the expressions, if it can involve undefined behavior, and if so, for which values. And when we compare, so undefined behavior means, well, it is not defined, so we can ignore those values. So that is why for solving it, we just check all defined values that they are the same. But we also need to check that the target function doesn't have additional undefined cases that were defined in the original. So I do this here as two different queries. We could build a bigger query to ask, but it's more efficient doing several small than one big. Control flow is also problematic. We cannot have control flow in equations. So here instead for an if then else, we use conditional select. That is an operation in the language we build equations from. For loops, we unroll the loops, currently 16 iterations. And if it enters the 17th iteration, it is marked as undefined behavior in that execution. So that works perfectly fine for functions like this. So what the tool will do then is that as long as n is less than 16, everything is defined, and it may find bugs there. But if you pass n is 17 or up in this function, it will say that it's undefined behavior, so I don't need to check anything. So it's not an optimal solution, but it's sort of good compromise. And so if you find bugs that happens in the 16 first iterations. So here, I reported a PR on this. Since this gets vectorized, the additions are done in a different order, which may cause signed overflow that were not in the original. So this one has been fixed. But one problem with my solution is it does not handle loops like this. The bug is there also, but here it always loops 32 iterations. So it's always undefined behavior. So just because my tool says everything is fine, is not necessarily true. Memory. Here it starts to be a little bit complicated. So I have written a blog post about this if you want the details. But the general idea is that I represent all bytes in the memory as a large array. So arrays in SMT solvers are pure functional lazy structures. So it's no problem having this 16 exabyte array. So each time you store a value in the array, you get a new array. So you need to change, lose and store so the correct input array is used. And there are lots of interesting problems of keeping track of the undefined behavior for out-of-bounds access and how to represent ranges and everything like that. In addition, GCC has a little bit strange semantics of memory that adds second layer of problems. I talked about that at the latest GNU Cauldron if you want to look deeper into that kind of problems. Okay, so the SMT solvers, they try all possible values. So this, of course, very large search space, so it might take forever. But SMT solvers have a clever method to actually prune that address space. So the idea is to look for conflict. So it knows that this bit is 0, this one is 1, then this bit must be 0. So it doesn't need to check 1 for that bit, and so on. So by using heuristics to find the interesting cases that prune the search space early, it can actually, for most cases, do a full search for a program. And even if it cannot do it, it can start by looking at the interesting cases first. So it's often the case that you have a really complicated function, but if there is a problem, it finds it. But it will take far too long to actually prove that everything is okay when it is okay. But if there is a problem, it's often find it. Okay, I'm being quicker than I have anticipated. But so this was the overview of the tools I've done. And you may not want to check bugs in GCC every day, but I think there are some use cases for this that may or may not be relevant for more normal software development. So one obvious case is when you are having your function, you are cleaning it up, you are optimizing it, and so on. Then you actually do not want to change the functionality. So you can use this kind of tool to verify that your hand-optimized, cleaned-up function actually do the same thing as the original. And I have a tool for that, so SMT check refine. Compares two functions as if one is an optimization of the other. Similarly, if you are optimizing a function to assembly, so you can provide the assembly to verify with instead of the GCC generated assembly by setting an environment variable. So one other thing is that when you generally want to test, you don't have out-of-bounds accesses and everything like that. So you can use sanitizers, Valgrind, and that kind of tools, but it only finds the problems that you are actually executing. So you can use fuzzers and so on to try to get good coverage. But it's annoying. But as I said, the SMT solver checks all inputs. So, of course, it has other problems that it often times out and so on. But when But as I said also that it often finds problem if they exist. So you can use, I have a plugin for this, SMT GCC Verify, that checks this kind of thing. This is very much work in progress, so it may not be completely useful today. But my plan is to actually work with this heavily the following couple of weeks, and I will talk about this in the coming GNU Cauldron in Prague, the days before Linux Plumbers. So I have not really figured out exactly what I want to check. So I can find undefined behavior, I can find a search failure, use of uninitialized memory, C++ contract violations, and that kind of thing. But I'm really interested if any of you have sort of a use case that I could use to also have as the target. So one paper that have inspired me is a thing that Amazon wrote 6 years ago, where they use this kind of tools to verify the hypervisor and IoT operating system and so on. They used CBMC, and they wrote contracts in C. So I think that using GCC as the background here is a good fit for that. Because if you look at the CBMC version, they need a lot of strange annotations and so on. But GCC already have much of that infrastructure with attributes. And adding those attributes like non-null, access, assume, and so on actually helps code generation, and it helps the GCC warnings and the F-analyzer static analysis tool. So you get things for free by adding this. Also, the GCC has lots of information about your program. So it can give hints to the SMT solver to start verifying the interesting path, and therefore be able to make it faster. Yep, so to wrap this up, the project is very much work in progress. It's very useful for me, but I'm not sure how well it works for someone who does not know the limitations. But I'm working on it, and please let me know if you have a potential use, and I'll try to prioritize that. So that's it.
Since this you could use it for doing analysis of assembly code, could it be used for comparing assembly version to assembly version?
Yes. So the actual infrastructure is there. The problem is how I set up the tools understanding of the memory layout and everything like that. I take that from GCC. So you need to add some kind of wrapper that does that work. But it's just a simple matter of programming. That
the idea was, of course, that trying to compare Clang with the GCC generated code.
Yeah. So in principle, it's a little bit about discussing how to have the user experience. The actual work to getting this working is not hard. So we can discuss it if you want to do this kind of analysis. I can add the functionality if we discuss exactly what you need.
Who's next?
Thank you for this great work. Much appreciated. I've found about 6 bugs in GCC in my career so far, and I'm happy that someone adds tooling that makes you find these bugs before they mess up your code and not days after you've spent all the time debugging. Back in the day, we've worked with tools like CSmith to randomly generate C programs and thus test the C compiler into compliance. I think maybe that it would be a wonderful combination with your tool. I hope everything will work out and you'll find lots of beautiful bugs in GCC.
So the current fuzzing tools like CSmith are not too useful to use with my tool because they usually set up hard-coded values for everything and then see that the result is the same. So my tool doesn't have the freedom to check all paths because they pass in 1, 5, 7. So, but using fuzzing is very good for this kind of thing. LLVM has a similar tool as mine, and they have found thousands of bugs by fuzzing. I have not had the time to work on any real fuzzing things, and I wrote some primitive fuzzing infrastructure. I find a couple of bugs, but not anything exciting. So what they do in LLVM side, they take essentially the test suite and then do random mutation of it, because the test suite have interesting cases, and then they mutate it so they get corner cases of the interesting cases. But doing that for GCC need somewhat, well, very different infrastructure. So I have not had time or energy of doing that yet.
Yeah, looking forward to seeing more work in this area. This is very good stuff. Who's next?
Thanks for presentation. My question from practice, actually. Would it be possible to compare the code for the same function, but between different versions of GCC? Because sometimes, for example, the older versions we have in Linux kernel, we have a minimum version of GCC, 8 point something. And a couple of months ago, it was a bug, and indeed for some architecture, it's exactly for, it's bug in GCC basically. But because we have minimum version, in any case, to prove that there is bug or there was bug. And
right. I can answer in 2 or 3 different ways. So if you want to compare between different versions of GCC, what you want to compare then is essentially that assembly is the same. Because you do not care if it is some random bug in the middle that gets cancelled or whatnot. So comparing the assembly, you could sort of already do by running it once normally and once with your substitute assembly with the old one. Also, if you want to verify that your old compiler works, so the GCC APIs are relatively stable, so you could compile my plugin for your old compiler. I'm always tracking top of trunk, so there may have been some minor things that need to be fixed up. But in that way, you can compile with GCC 10 or whatever and see if what bugs get my tool finds in when you compile using that one.
yeah, but the problem with comparing assembly, that assembly could be really different between different versions for the same function.
Right, but that they are very different doesn't matter. The difference is the functionality. My tool will say that, okay, they give the different result. So my tool translates the function to formal logic. and then verifies that they work the same way. So, so that works fine. And you can say in some sense that is what I do when I report some of these bugs. I compile it with GCC and I say this function is assembly is wrong. I guess it should have been something like this, or couldn't this have been vectorized like this? And I do that, and okay, can I open a bug that okay, you could have vectorized it instead of no. So, but that said, the more different the code is, the slower the tool is, and there are lots of things I know how to improve performance. But so I probably need to do some more optimization work before this is a good use case. But I think you can do some of that already today.
Next question. Thank you for your work to start with. About undefined behavior. Most undefined behavior in C is actually defined if you know the target. Can you specify this in your tool?
Sort of, yes. On the other hand, GCC different GCC passes, since it knows it's undefined, it can do stupid things. So just because the target does in a certain way doesn't mean that everything is okay.
For example, in UC standards, the latest one, I think, it demands the target to be in two complements form for negative,
right.
Which solves like half of all the undefined behaviors.
Right. I didn't prepare an example. But for example, in one of the bugs I reported, changed the order of addition. So, which means that they can overflow in different ways. So if you look at the add instructions, that doesn't matter at all in two complements and so on. But if you had an if x is larger than 0 after everything, GCC decided to use a different comparison instructions that set up different condition flags in a different way, that assumed that it didn't wrap.
Okay, so you can't tell it, for example, if you shift a negative value,
Yeah.
it's undefined, but in most targets, it's very defined.
Right, but GCC can decide that it can do something.
But you can't tell your tool to, well, yeah, I know this is undefined, but it will become this.
You cannot tell GCC that in general. You can for certain values, so for that, it does the right thing. And when I model the assembly, I model the assembly as actually the CPU do. But in the GCC internal representation, GCC knows that only these values are defined. So if it can improve performance by ignoring that. So for example, if it knows that a value is positive, and it knows that two values are positive, you multiply them together, or add them together, or whatnot, and then shift the result. Then, sorry, let me say it correctly. If you have two values, GCC knows are positive. You add them and divide by 2. The addition could have overflowed, which makes it negative. But GCC still generates code as it thought that the addition is positive. So the division by 2 can be a shift instead of the division operation.
The question is whether it's logical or at least.
Yeah, sort of. So, but that means that just because the CPU does something doesn't mean that GCC doesn't take advantage of the undefined behavior.
assumptions and do something else. For example, it can simply generate undefined instruction.
I'm working with audio, and you have negative numbers, and you do all kinds of math on negative numbers, and yes, that's super works.
Yeah. More questions?
Does it work on all of the GCC frontends, and can you compare code between different languages?
So I work on the middle end passes. So in some sense, it works with all of the front ends. But some front ends may use sort of language-specific operations that I do not know about. And if you take, for example, Fortran, have very much pointer accesses and so on with restrict and so on, that my restrict handling is really limited now, which makes it very slow. So it sort of works, but it's dramatically slower than what it could be. But so you should be able to take any language, but you may get a large number of warnings that my tool doesn't understand certain things and so on. But, so I'm only testing C and C++.
Right. Okay. Then it's probably time for a photo, group photo.
Yeah, thanks.
So thank you, Krister.